Chapter 32 Light, Reflection, and Refraction. Units of Chapter 32 include the ray model of light, reflection, image formation by a plane mirror, formation of images by spherical mirrors, index of refraction, Snell's law, visible spectrum and dispersion, total internal reflection, fiber optics, refraction at a spherical surface. Section 1. The ray model of light. Light very often travels in straight lines. We represent light using rays, which are straight lines emanating from an object. This is an idealization, but is very useful for geometric optics. So if you have an object and you're looking at an object, rays of light from the object are emanating in all different directions, including the direction toward our eyes. Therefore, some rays from this object are reaching to our eyes and forming the image of the object, which is a pencil here, for example. Section 2. Reflection, image formation by a plane mirror. Law of reflection says the angle of reflection that the ray makes with the normal to the surface equals to the angle of incidence. So if we have a plane mirror, the angle that the incident line is forming with the normal to the surface is equal to the angle that the reflected ray is forming with the normal to the surface. We call the angle of incidence theta I and the angle of reflection theta R, and these two angles are equal. It might be a little clear from the side view that we can see a cross-sectional side view from a plane mirror, and rays of incident light are bouncing off from the mirror at the same angle that these rays are reaching to the mirror. When light reflects from a rough surface, the law of reflection still holds, but the angle of incidence varies. This is called diffuse reflection. As we see, for a rough surface, we don't have a plain, flat surface. Therefore, different rays of light, which are in parallel reaching to the surface, they are bouncing off in different random directions because of the roughness of the surface. Different rays of light are reaching different surfaces, and therefore, the reflected rays of light are bouncing off at different random angles. With diffuse reflection, your eye sees reflected light at all angles. With specular reflection, from a mirror for example, your eye must be in the correct position. For this cartoon, we have a rough surface, and we can see some rays of source are bouncing off from the surface and reaching to our eye, no matter where our eye is located. For a specular reflection off from the mirror, for example, if you have a source, a bunch of rays of light are reflected off from the surface, and they are going only to one direction, and they're forming an image only at a particular location where our eyes should be placed. What you see when you look into a plane or flat mirror is an image, which appears to be behind a mirror. Here we have a bottle as an object. The rays of light from this object are reaching to the mirror, bouncing back from the mirror, goes to our eye. But what our eye is seeing is actually the extension of these rays of light into the mirror, represented with a dashed line, and it looks like as if the object is inside the mirror. But that is the image of the object into the mirror. This is called a virtual image, as the light does not go through it. The distance of the image from the mirror is equal to the distance of the object from the mirror. As an example, let's take a look at problem number 4 in the book. A person whose eyes are 1.64 meter above the floor stands 2.66 meter in front of a vertical plane mirror whose bottom edge is 38 centimeter above the floor, as shown in the figure down here. What is the horizontal distance x from the base of the wall supporting the mirror to the nearest point on the floor that can be seen reflected in the mirror? To solve this problem, let's draw some diagram for the rays and object to visualize this problem better. So this is the floor, this is the mirror placed at distance h, and this is the object or the person in front of the mirror, capital H. The angle of incidence is the angle of reflection, so we say the highest point of the person or the object will reach to the lowest point of the mirror at the same angle, bounces off from the mirror, and we imagine that to the ground at the same angle of theta. So this angle is the same as this angle and is the same as the incident angle on the mirror. So once again, this is the mirror, this is the person, and the distances are x, and the person is standing at the distance L from the mirror. The question is asking about the distance x. So we have tan theta from geometry is equal to h minus h, this distance, over L. And this is equal to h divided by x. So from this relation for the geometry, therefore, x is equal to HL, capital H, minus little h. We have, plug in the numbers, 0.38 meter multiplied by 2.6 meter divided by 1.64 meter minus 0.38 meter. And that gives us x equals to 0.78 meter for this problem. Okay, let's look at another problem from the book, problem number 8 as an example. Stand up two plane mirrors so they form a 90-degree angle as shown in the figure below. When you look into this double mirror, you see yourself as others see you instead of reversed as in a single mirror. Make a ray diagram to show how this occurs. To answer this problem, look at the figure and imagine that we are looking at the top view of this clock being seen into the mirror. This situation is depicted in this diagram for the rays. Number 3, for example, is reflected off these two mirrors, goes to the eye, but it's actually a virtual image formed down here. Same story for number 9, is bouncing off from these two mirrors, coming into the eye, but it's actually being formed as a virtual image down here. What we see in the mirror is actually a not reversed image, or not the mirror image of the actual object. Section 3. Formation of images by spherical mirrors. Spherical mirrors are shaped like sections of a sphere and may be reflective on either the inside or outside, and we call them concave or convex respectively. On part A on the left, you'll see a cartoon for the convex mirror where the light is being reflected off from the outside of a spherical mirror. Parallel rays of light coming from distance, and they are bouncing off with the same angle as the incident angle. For a concave mirror, some parallel rays of light are bouncing off from the inside of a sphere. The reflection law still holds, and the angle of incidence is equal to the angle of reflection. Rays coming from a faraway object are effectively parallel. So we have an object in the far. Rays of light are diverging out from this object, but if you're looking at a far distance, the rays of light are considered parallel. Parallel rays striking a spherical mirror do not all converge at exactly the same place if the curvature of the mirror is large. This is called spherical aberration. Due to the curvature of this mirror, parallel rays of light are not converged on the same spot, and this is called spherical aberration. If the curvature is small, the focus is much more precise, and the focal point is where the rays converge. So this is only a portion of a sphere. This is the center of the sphere, and we have a focal point, and the rays of light are focused on focal point, which is not the center of the sphere. Using geometry, we find that the focal length is half the radius of curvature. F as the focal point, 1/2 of R is the radius of curvature for a spherical mirror. Spherical aberration can be avoided by using a parabolic reflector. These are more difficult and expensive to make, and so are used only when necessary, such as in research telescopes. We use ray diagrams to determine where an image will be. For mirrors, we use 3 key rays, all of which begin on the object. The first one is a ray parallel to the axis. After reflection, it passes through the focal point. The second ray is a ray through the focal point. After reflection, it will be parallel to the axis. And the third ray, a ray perpendicular to the mirror, and it reflects back on itself. The image is formed at the intersection of all these 3 rays. So here we have a cartoon showing these 3 rays that we just mentioned. For part A, we have ray 1 from an object parallel with the axis connecting the center of the spherical mirror to the mirror. This ray is reflected off from the spherical mirror and is passing through the focal point, F. The second ray is passing through the focal point and is reflected off from the curved mirror in a way that it will be parallel to the axis. The third ray will be normal to the spherical mirror and is reflecting off from the spherical mirror, and it overlaps on its original ray, and it passes through the point C, center of the curvature. All these 3 rays are intersecting at point I prime. This is a point where the image will be formed. The intersection of these 3 rays gives the position of the image of that point on the object. To get a full image, we can do the same with other points, and 2 points will suffice for May purposes. Geometrically, we can derive an equation that relates the object distance, image distance, and focal length on the mirror. As we define, F is the focal points or focal length of the curved mirror, DO is the distance of the object, and DI is the distance where the image will be formed. And the relationship says 1 over the distance of the object plus 1 over the distance of the image from the mirror is equal to 1 over F, the focal length. We can also find the magnification, the ratio of image height to the object height, as M, the ratio of the height of the image divided by the height of the object, and is equal to minus the distance of the image divided by the distance of the object. The negative sign indicates that the image is inverted. This object is between the center of the curvature and the focal point, and its image is larger, inverted, and real. If an object is outside the center of curvature of a concave mirror, its image will be inverted, smaller, and real. So this is your face looking at the concave mirror, but at a farther distance from the center of the curvature. If you draw the three rays, one is passing through the center of curvature, one is passing through the focal point, and one is in parallel with the axis, and it's passing through the focal point. These three rays will intersect at this point, and this is the place of the image will be formed. And this image, as you can see, is real because it's formed with the real rays of light, and it's inverted and is smaller. For a convex mirror, as the rays are diverging, the image is always virtual, upright, and smaller. So if the object is far away in infinity, all the rays will be diverging, but the rays can be traced and intersected at a focal point F where the image will be formed. So wherever the object is placed in front of the convex mirror, the image will be formed virtually, and it's upright, and it's always smaller. So for solving problems with spherical mirrors, we have to pay attention to these 4 points. 1. Draw a ray diagram. The image is where the rays intersect. 2. Apply the mirror and magnification equations. 3. Sign convention is if the object, image, or focal point is on the reflective side of the mirror, its distance is positive, and negative if otherwise. Magnification is positive if image is upright, and negative otherwise. 4. Check that your solution agrees with the ray diagram. Section 4. Index of refraction. In general, light slows somewhat when traveling through a medium. The index of refraction of the medium is the ratio of the speed of light in vacuum to the speed of light in the medium. So we define n as the index of refraction, and it's the ratio of the speed of light in vacuum, c, divided by the speed of light in the medium, v. The table on the right is listing some indices of refraction for some materials. For vacuum, it will be 1 because v is equal to c. For air, in STP condition, the index of refraction is 1.003. For water, it is 1.33. And we have higher index of refractions for alcohol, different glasses, sodium chloride, and for example, for diamond, it will be 2.42. These values depend on the wavelengths of the light, and here we're talking about the wavelengths of red light, 589 nanometer. Section 5. Refraction, Snell's law. Light changes direction when crossing a boundary from one medium to another. This is called refraction, and the angle outgoing ray makes with the normal is called the angle of refraction. For example, for the case where the light is traveling from low refractive index to a more dense material and higher index of refraction, for example, from air to water, the incident ray is bending toward the normal. The reflected light has the same angle with respect to normal as the incident angle. For the other scenario, where the light is coming from larger index of refraction to a lower index of refraction, for example, from water N1 to air N2, the light is bending away from the normal to the surface. As you see here, the refracted ray is bending away from normal. So theta 2 is larger than theta 1. However, the angle of reflection is the same as the angle of incidence. But the angle of refraction, theta 2, is larger than the angle of incidence, theta 1. Refraction is what makes objects half submerged in water look odd. You might have noticed by looking at someone inside a pool, if you look at them, they might seem that they have short legs, but it's actually an outcome of the laws of refraction. The angle of refraction depends on the indices of refraction and is given by Snell's law. The index of refraction in medium 1, n1, multiplied by sine of the angle of incidence in medium 1, theta 1, is equal to the index of refraction in medium 2, n2, multiplied by the sine of the angle of refraction in the medium 2, theta 2. As some examples, I'll look at some problems from the book. First, I'll look at problem number 12. The lateral magnification of a convex mirror is plus 0.75 for objects 3.2 meters from the mirror. What is the focal length of this mirror? To solve this problem, we use equation 32-2 and 32-3 for magnification as minus the distance of the image divided by the distance of the object, and solve it for the distance of the image is equal to minus magnification times the distance of the object. Also, we have a relation for the distance for the object plus 1 over the distance of the object is equal to 1 over the focal length. We can solve it for the focal lengths. F equals to dO di divided by dO plus di. The substitute for di is dO minus mdO divided by dO minus mdO. That gives us, that simplifies as F equals to m dO divided by m minus 1. Let's plug in the numbers. We have magnification of 0.75 multiplied by 3.2 meter divided by 0.75 minus 1, and that gives us minus 9.6 meter. This is the focal point of the convex mirror. Another example, problem number 20 in the book. The image of a distant tree is virtual, very small, and 13 centimeter behind a curved mirror. What kind of mirror is it, and what is its radius of curvature? The tree is in a far distance, so the distance of the object is infinite. The distance of the image is minus 13 centimeter because the image is behind the mirror. Okay, let's plug in the values in equation 32-2. 1 over the distance of the object, 1 over the distance of the image is equal to 1 over the focal length. If we plug in the values, we have 1 over infinity plus 1 over di is equal to 1 over f. 1 over infinity is 0, and we have f is equal to di. Di is minus 13 centimeter. Therefore, the radius of curvature is 2 times the focal length, that is equal to minus 26 centimeter. Another example, problem number 24 from the book. In example 32-4, show that if the object is moved 10 centimeter farther from the concave mirror, the object's image size will equal the object's actual size. Stated as a multiple of the focal lengths, what is the object distance of this actual size image situation? When the object distance is changed from 20 centimeter to 30 centimeter, the radius of curvature is still 30 centimeter, right? So the focal distance will be 15 centimeter. Just plug in these values. 1 over d object plus 1 over d image is equal to 1 over f solve it for di is equal to d object multiplied by f, d object minus f is equal to 30 centimeter multiplied by 15 centimeter divided by 30 centimeter minus 15 centimeter, and that gives us 30 centimeter. So the magnification is equal to minus di over d object is equal to minus 30 divided by 30, and is equal to minus 1. We see that the image is inverted because magnification is negative, and the same size because the magnification is equal to 1. So the object is 2f for this actual sized image situation. Section 6. Visible spectrum and dispersion. The visible spectrum contains the full range of wavelength of light that are visible to the human eye. As I mentioned earlier, the visible spectrum covers nearly 400 nanometer to about 750 nanometer. From the blue color, green color, yellow toward the red, and electromagnetic waves at larger wavelengths or less energy are called infrared, and wavelengths below 400 nanometer are called ultraviolet. The index of refraction of many transparent materials, such as glass and water, varies slightly with wavelength. This is how prisms and water droplets create rainbows from sunlight. So a white light is composed of different components of color. If you send a white light through the prism, different wavelengths are refracted at different angles, and they will be separated on a wall or screen, and you will see a rainbow pattern, which the same story happens when we have droplets of water instead of the prism. This diagram shows the variation of the refractive index for different glass materials with respect to wavelengths. This spreading of light into the full spectrum is called dispersion. This is a cartoon showing when the sunlight is refracted and dispersed through water droplets at different height and different altitudes. We will have different rays of light at different color will be refracted into our eye. For example, on higher altitudes, we have violet refracted and is going away from our eyes, but only red rays are refracted and diverged, and they come into our eyes. At lower altitudes, lower heights, we have sunlight refracted, and red lights do not go to our eye, but more like violet colors and blue colors reach to our eye. Therefore, what we see is red color on the top and different colors up to violet color, forming the rainbow. Let's look at problem number 36 from the book as an example. The speed of light in a certain substance is 78% of its value in water. What is the index of refraction of that substance? So to find the index of refraction, let's use the equation for the index of refraction, equation 32-4, which says index of refraction is equal to the ratio of C over V, and the velocity is 78% of the velocity in water. Let's write down the same equation for the index of refraction of water is C over velocity of water, and let's solve it for velocity of water is equal to C divided by index of refraction of water, and we can plug in this value into this equation, and index of refraction of unknown substance is equal to C divided by 0.78 times C divided by index of refraction of water. The speed of light cancels out, and we will have index of refraction of water, which is 1.33 divided by 0.78. That gives us index of refraction of 1.70 0.05, almost 1.7. Section 7. Total internal reflection, fiber optics. If light passes into a medium with the smaller index of refraction, the angle of refraction is larger. There is an angle of incidence for which the angle of refraction will be 90 degrees. This is called the critical angle. So if you write down the Snell's law in a way that the sine of the critical angle is equal to the index of refraction of the second material over the index of refraction of the first material multiplied by the sine of 90 degrees, which is equal to 1. That gives us the ratio of N2 over N1. If the angle of incidence is larger than this critical angle, no transmission occurs, and this is called the total internal reflection, because all the light will be reflected off the intersection of the two materials. Here, at angles lower than the critical angle, the light will be refracted. As the angle is approaching the critical angle, the light is bending more and more up to the level at the critical angle. The light is not transmitted into the other medium, but is only transmitted at 90 degrees with respect to the normal to the boundary of the two medium. At an angle of incidence larger than the critical angle, all the ray will be reflected off the boundary between the two media. And this is called the total internal reflection. Binoculars often use total internal reflection. This gives true 100% reflection, which even the best mirror cannot do. Optical fibers also depend on total internal reflection. They are therefore able to transmit light signals with very small losses. As an example, let's go through problem number 44 in the book. In searching the bottom of a pool at night, a watchman shines a narrow beam of light from his flashlight 1.3 meter above the water level onto the surface of the water at a point of 2.8 meter from his foot at the edge of the pool, as depicted in this cartoon down here. Where does the spot of light hit the bottom of the pool, which is 2.5 meter deep? Measure from the bottom of the wall beneath his foot. First off, we say tangent theta 1 is equal to L1 over H1, and where L1 is 2.8 meter, and this is L1, and H1 is 1.3 meter, and that gives us 2.1538, and we can solve it for theta 1, and that is equal to 65.095 degrees. For the refraction from air into water, we can use Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. For N1 we have air, for N2 we have water, and we can solve it for theta 2. So let's plug in the numbers. For air we have 1 sine theta, theta is 65.095 degree. For N2 we have water is 1.33. Sine theta 2, do the math, theta 2 will be 42.997 degrees. The horizontal distance from the edge of the pool can be calculated with L is equal to L1 plus L2, and that is equal to L1, we know it, is the place where the light is going to be shined, plus H2, tangent of theta 2. That is equal to 2.8 meter plus 2.1 meter multiplied by tangent of 42.997 degrees. And that gives us 4.758 meter, almost 4.8 meter away from the edge of the pool. Section 8. Refraction at a spherical surface. Rays from a single point will be focused by a convex spherical interface with a medium of larger index of refraction to a single point, as long as the angles are not too large. So here we have an object, distance d from the spherical surface. The ray is striking the object at an angle alpha, and the ray is forming angle theta 1 as the angle of incidence with the normal to the spherical surface, and the ray is observing some refraction as it goes from the air to the glass, for example, bends toward the normal to the surface as it's refracted and hits the axis at point I. Geometry gives the relationship between the indices of refraction, the object distance, the image distance, and the radius of curvature. So we have index of refraction in medium 1 divided by d of object, is the place where the object is placed, plus the index of refraction for spherical object divided by d for image, that is equal to the difference between the indices of refraction, n2 minus n1, divided by r, the radius of curvature. For a concave spherical interface, the rays will diverge from the virtual image. Here is an object. We have a ray from the object, and it will diverge as it refracts, but we can extend from the tail of the object, the dashed line indicated here. At this point, the image will be formed because it's not with the actual rays of light. This is a virtual image. So we have d for object, the distance from the object to the spherical surface. We have d, distance for the image from the spherical surface, and r, the radius of the curvature for the concave spherical interface. Summary of Chapter 32. Light paths are called rays. Index of refraction is defined as the ratio between the speed of light in vacuum over the speed of light in the medium, c over v. Angle of reflection equals angle of incidence. In plane mirror, image is virtual, upright, and the same size as the object. Spherical mirror can be concave or convex. Focal length of the mirror is half of the size of the radius of curvature. Mirror equation is given by 1 over distance of the object plus 1 over the distance of the image is equal to 1 over the focal length. Magnification is defined as the ratio between the height of an image divided by the height of an object, and is equal to minus the distance of the image from the mirror divided by the distance of the object from the mirror. Real image is light passes through it. Virtual image is when light does not pass through. Law of refraction, or Snell's law, is given by n1 sine theta 1 is equal to n2 sine theta 2. Total internal reflection occurs when angle of incidence is greater than the critical angle. The critical angle is given by sine of theta critical, theta c, is equal to n2 divided by n1.